So we'll try and cover the theory of maxima and minima. Imagine if the addition of two numbers is given to you as, let us say, 12. Right now I'm assuming that these numbers are natural. I want to see, yeah, let us say a plus b is given to us as 12. A comma b are natural numbers, and I want to see what kind of pattern does a into b follow. So if I take this 11 and 1, I have the product as 11. If I take these as 2 and 10, I have a product of 20. If I take these as 3 and 9, I have a product of 27. If I take it as 4, 4 and 8, I have a product of 32. Now observe, as you start to distribute 12, as the numbers a and b are approaching closer, the product is increasing. So 12 I can distribute equally as 6 and 6. So 36 is the largest product I can expect. If I reduce this by one step, if I take it as 5 and 7, look at this, the product has reduced. So what was I trying to convey with this example? I was trying to tell you guys that product of numbers are maximized if the numbers are made equal. Now, one critical condition is there that usually people do not follow or do not know. That condition is, guys, addition must be given constant, then only these properties will work. These properties are designed for positive numbers, not necessarily natural. I wanted you guys to start with the easier problem, so I assumed them to be natural. Imagine if I have a plus b as 23 and somebody asks me maximize a into b. What I will do is I'll make this number 23 by 2, I'll make this number 23 by 2, and I will have 23 by 2 whole square as the maxima. But if same question has been created with a condition that a comma b should be natural, if you come across such a condition, you will have to work with manual values. If I say a plus b is 23, the closest possible breaking of the term is 11 and 12, and a into b is 132. Now understand, this was because the natural number condition was there, so I have to do this manually. If that condition is not there, this is absolute maximum of the product a into b. So I want you guys to copy down both examples, and second example with condition 1, condition 2. These theorems are designed for positive numbers. What is the crux of the theorem? That products can be maximized. Product of numbers can be maximized if the terms are made equal, provided, the most important condition, provided addition is given constant. Without addition given constant, this theorem will fail. Let us think reverse. That product of numbers is 144. It has been given to us that a and b are natural numbers, and I am worried about the pattern of a plus b. So I can take this as 1 into 144, addition is 140. I can take this as 2 into 72, addition is 74. 3 into 48, addition is 51. You guys might have predicted by now what is happening to the sum. See, 5 is not a factor, 6 is a factor. 6 is a factor how many times? 24 times, the sum is 30. Do you see, as I start to bring a and b closer, the addition has started to fall. The closest possible breaking of the number is 12 and 12. So the smallest possible addition is 24. See, if I step back by one step, if I write this as 9 into 16, the addition is 25. It is still more than 24. So what was I trying to convey here with this example? I was trying to tell you that addition of numbers is minimized if you make numbers equal. The most critical condition is for any of this to work, the product of numbers must be given constant. Now, again, I started with the easier term, natural numbers. What if I have a product of A and B here as an example, where it is not a perfect square? Let us say A into B is 72. Now, if you want the minimum possible value of A and B, you want the minimum possible value. A and B are real numbers, that is the positive real number, that is the only condition given to us. Then you assume this as a variable x into x is equal to 72. So x is equal to root over 72. So A and B both are equal. So 2 root over 72 is the answer, guys. You take x is equal to root 72 and you put in A and B. Now, if the same example is framed with the condition that A into B is equal to 72 and A comma B are natural numbers, minimize the addition of A and B. In this case, I have to manually break down these numbers. Now, with trial and error, I can say the closest possible breaking of numbers is 8 and 9. So 8 into 9, 72, 8 plus 9, 17. This is the minimum condition provided they are natural numbers. But if you compare, you will find root over 2 root over 72 is less than 17. How can you verify that? You square both and you can compare. If not, you use a calculator and perform the square root of this, make it double. You will see it is below 17. Now, there is something that connects both of these theorems. That is, A and B need to be positive real numbers. Now, another thing that connect both these theorems is that you are trying to make these numbers equal. Now, please pay attention. Products, multiplications are maximized. Additions are minimized when you make them equal. For the first one to work, addition should be given constant. For the second one to work, product should be given constant. Now, if I do not see the condition of natural numbers, there is one more way to approach this kind of problem or these kinds of problems. So that concept is arithmetic mean of numbers is more than or equal to geometric mean of numbers is more than or equal to harmonic mean of numbers. In CAT, so far I have not come across a question involving comparison of a harmonic mean. But the first two comparisons are very common and very frequently seen in exams like CAT, XAT, SNAP, IFT. What is that comparison? If I say A and B are two numbers, then the arithmetic mean of these numbers is more than or equal to their geometric mean. What is geometric mean? Square root of their product. If I have three numbers A, B and C, then arithmetic mean. What is arithmetic mean? The normal average. Addition upon the number of terms is more than or equal to cube root, guys. Because there are three terms, cube root of A into B into C. If I have four numbers, this will be more than fourth root over of A into B into C into D. I want you to copy down these results first. Then I'll tell you how does this theorem or these steps fit our requirement here and why additions are minimized and why products are maximized. How does all of this fit the requirement here? Understand, let us talk about A plus B is equal to 24 and A into B is required. Maxima is required. So addition is given, that means the arithmetic mean part is given to you indirectly. So 24 by 2 is the arithmetic mean. is more than or equal to square root of a into b. So if I rearrange this for you, I will have 12 ka square more than equal to a into b. So 144 is more than a into b. Now understand, the product a into b is equal to 144 or below 144. So when you make it equal, you have taken the maximum value a into b can take. Because, understand, because geometric mean is on the lesser side, on the smaller side, you are able to maximize it by making it equal to 144. Please observe. If in this case, reverse, if a into b was given to us as 36, I will say a plus b upon 2 is more than or equal to square root of 36. So a plus b is more than equal to 12. See, a plus b is either equal or more than 12. That means when you make it equal to 12, you are assigning it the minimum value possible. Understand, additions are on the upper side. See, this is the larger value than root of 36. So when it becomes equal, it takes the minimum. That is the reason additions are minimized, because they are on the upper side, and products are maximized because they are on the lower side. Now, this method and this method internally is making a and b equal. Luckily, I have assumed numbers which give me natural outcomes. These methods do not care about values being natural or not. Observe, if I give you a plus b as 13, and if I ask you for a into b maximum, please observe, this will be 13 by 2 more than or equal to square root ab. So 169 by 4 more than equal to ab. Your job is done. These methods, or this particular method, does not care about values being natural or not. This method only cares for values being positive. Positive real numbers are there, this will work. A into b is, let us say, 24. Then a plus b upon 2 is more than or equal to root over 24. So a plus b is more than or equal to 2 root 24. I hope you understand when to apply which method. The first method, that you saw, depended upon you being able to equalize a and b. Second method is making these values equal by default without letting you know. So internally, this method is also making these terms equal. Now, this was the very elementary part of maxima minima for algebraic terms. Let me extend this to terms like 2x plus 3y is equal to 25 and x cube into y square is to be maximized. The condition is x and y are positive real numbers. I want you guys to first write this down as a question. For the equation 2x plus 3y is equal to 25, x and y being real numbers, positive real numbers, maximize x cube into y square. Write this down. Now follow these steps carefully. Now these are the questions that you will come across in CAT as applications. You will rarely come across a direct question on this. This will be part of some question, some steps, some calculation. The approach here, guys, is, see, this representation means x has been multiplied 3 times. This representation means y has been multiplied 2 times. So here it is your job to create 3 terms of x and 2 terms of y. How is that done? Observe, 2x divided by 3. There will be 3 such values. And 3y. See, this coefficient and this coefficient has nothing to do with the step. The number of divisions is decided by power in the product. So products determine how many terms you will create. This will become 3y by 2 and 3y by 2. Now all these terms are equal. If all these terms are equal, you are basically asking for this and this to be equal. Now if these are equal, they must be equal to something. Let us say k. That gives me 2x is equal to 3k, 3y is equal to 2k. Please observe, this value and this value can be directly put in this equation. This number, this equation, or this term 2y is equal to 3k, and this term 3x is equal to 2k is equal to 25. That gives me k is equal to 5. Now please observe, if you have the value of k, your job is done here. X is equal to 15 by 2, y is equal to 10 by 3. For these values, the product is maximized by default. So 15 by 2 cube multiplied by 10 by 3 square, your product is maximized. If you can cancel some terms, do that. 15 is 3 into 5, so 3 cube into 5 cube. 10 is 2 into 5, so 2 square, 5 square divided by 2 cube into 3 square. Whatever you find that can be cancelled, cancel it out. Cancelled, cancelled, 3 ki power 1 remains. Cancelled, cancelled, 2 ki power 1 remains. So what you basically have is 3 multiplied by 5 to the power 5 divided by 2. Guys, this is your answer. Now I'll scroll up. I wanted to copy this down. Here you get one more important result. For this to be maximized, you are able to find out at what values of x and y. Only one step that is critical here is sentence. Product. Product determines the number of terms to be created. I had x ka cube I had. So I must divide whatever is the term of x with 3. Y I had a square. So I must divide y wala term with 2. This method helps us in finding out at what values of x and y is the minima or the maxima being achieved. That is the benefit of this method. See, one more thing. Once you make it equal to k, do not cancel the coefficient of x and y. It is going to fit the equation perfectly. This method will work for the scenario where the product has been given to you and addition has to be minimized. Again, guys, additions are minimized and products are maximized. While the question here was, if 2x plus 3y is equal to 25, where x and y are positive real numbers, then find the maximum value of x cube multiplied by y square. Again, even in CAT, you will rarely come across a direct question like this. It will be part of either a shopkeeper is selling marbles in packets. For every increment of 10 marbles, the price of marbles goes down by 5 paisa. What is the optimum size of the packet to make the maximum revenue? Or from a rectangular sheet of paper for given dimension, a square corner is cut from every corner and then it is folded to form a rectangular box. How to maximize the volume? Or in a solid cone, from a solid cone, a cylinder is to be cut out. How can we maximize the surface area of the cutout cylinder, or how can we maximize the volume of the cutout cylinder? Such questions are pretty common in CAT. Whenever you come across a equation of the form ax plus by is equal to some number, so let us say c, and you have x ki power a and y ki power b. In this case, let us take this as capital A and capital B to avoid confusion. Here, ax by a should be same as by by b. Whatever is in the power will divide the term in the addition. That's it. You equate with something and then you replace it back. This theorem is universal for these kind of problems. If this is not given constant and this is given constant, it will still work. You need to find the value of x and y and then put it back. So guys, this is basic theory behind maxima minima. Internally, numbers are being made equal. We are not trying to make it equal. The A.m G.M concept is making these numbers, these values equal internally.